Hello everybody. Today in this video we're going to see our solution for exercise 4, an exercise on the set of complex number. So let us begin. The first question is on finding the argument of this complex number, which is z is equal to 3i over minus 1 minus i. So that to do this, first we have to simplify that. That means we must write it in the standard form, just in within the real and the imaginary part of this expression. So z is equal to minus 3i over minus 1 minus i multiplied by, we have to multiply both the numerator and the denominator of this one by the complex conjugate of the denominator, which is minus 1 plus i. So that it could be 3i into minus 1 plus i over the product of any two complex conjugates of numbers or simple complex number could be the square of their normal, so that it becomes 1 plus 1, which is 2. Therefore, when we further simplify this thing, we have 3 minus 3i minus 3 over 2, because here I square is minus 1, so that minus 1 times 3 becomes minus 3. Therefore, the standard form or simplified form of this complex number could be minus 3 over 2 minus 3 over 2i. And it could be written as minus 3 over 2 into 1 plus i. So that in the polar form, the magnitude or simply r of this complex number could be 3 over 2 times the square root of 1 squared plus 1 squared, which is radical 2 over 2. And then the argument, it is the tan inverse of an angle that's simply, which is the ratio of the imaginary and the real part of the complex number, that is minus 3 over 2 over negative 3 over 2, which is equal to positive 1. But that since both the real and the imaginary parts of the complex number are negative, so that the point that's simply which is determined by the imaginary and the real part of the complex number is standard quadrant. And therefore, the argument could be theta, which is equal to pi plus pi over 4, which is equal to 5 pi over 4. Second, again on the complex number, that's find the argument of z is equal to the square root of 3 minus I in the power of 6. So like the thing that already we have done in the first question, first we have to simplify this question, or simply the given complex number first. So that in order to further simplify this one, let's apply the polar form of the given complex number, since we have the exponent that's simply 6 here. So that in order to write the polar form of the given complex number, we have to determine the r and the argument of the complex number itself. So that in this case, first, r is equal to the square root of the real part of the given complex number, which is enclosed by the bracket. That means the square of the square root of 3 plus minus 1 square, which is equal to the square root of 3 plus 1, that is 4, which is the square root of 4, which is 2. So that theta in this case could be minus pi over 6, that is theta of the inner, that is radical 3 minus I, since theta is equal to negative 1 over 3, negative 1 over radical 3, which is in the fourth quadrant, since the real part is positive and the imaginary part of the given complex number is negative, so that the point must be in the fourth quadrant. That's why we take theta to be a negative angle. Then the Euler form, or simple Euler form of this one could be, that is radical 3 minus I is equal to 2 times e the power of minus I pi over 6. Minus pi over 6, that is minus pi over 6 because it is just negative pi over 6 here. So that z could be because already z is simplified to this form, that is 2 times e the power of minus 6 minus pi over 6, the power of 6, which is equal to, that is r to the power of 6, or to the power of 6 times e to the power of minus pi, that is minus I pi times 6 could be already minus I pi, which is equal to 64 times e to the power of negative I pi. This 64 is obtained from to the power of 6, that is r to the power of 6 of the complex number. And thus z is equal to negative 64 real and negative number. And so that the argument could be argument of z is equal to pi or negative pi, since it is on the horizontal axis, so that the angle could be pi or negative pi. The next question number 2a, we are asked just to show that the norm of e to the power of I theta is equal to 1. And then for e to the power of I theta, we have, or simply we know that this one that is cos theta plus I times sine of theta, which is an Euler formula. So that in this case, the solution that's simply the norm of e to the power of I theta is equivalent to the norm of cosine of theta plus I times sine of theta from this equation. So that the heat equivalent with the real part of this complex number is cos theta and the imaginary part is sine theta, so that its norm could be the square root of cos square theta plus sine square theta. And by using that of trigonometric identity, cos square theta plus sine square theta for a certain angle theta, an arbitrary angle that theta, that means is already 1, so that this could be the square root of 1, which is 1. Therefore, there is the proof that is the norm of e to the power of I theta is always 1. Next, we are asked just to show that the complex conjugate of e to the power of I theta is equal to e to the power of minus I theta. Therefore, just we have this one that is e to the power of I theta is equal to cosine of theta plus I sine theta. And the complex conjugate of this could be, that is e to the power of I theta bar is equal to cosine of theta minus I sine theta, taking only this one, the imaginary part of the complex numbers to be negative. And then, but cosine of theta is equal to cos theta, since cos theta is an even function, and sine of negative theta is equal to minus sine theta, since sine theta is an odd function, so that e to the power of negative I theta is equal to cosine of minus theta plus I times sine of negative theta, which is equal to cosine of theta. Just we have said here, because cosine of negative theta is equal to cos theta, and minus I times sine theta, because just we have said here, sine of negative theta is equal to negative sine theta, since sine theta is an odd function. Thus, e to the power of I theta bar, or the complex conjugate of this complex number, is simply the same as e to the power of minus I theta. Question number 3. We are given this one, that is using mathematical induction. We are asked just to show that e to the power of I theta 1 times e to the power of I theta 2 times e to the power of I theta n is equal to e to the power of I into theta 1 plus theta 2 plus theta 3 for n is running from 2 to that of any number of angles at n. To do this, we have an Euler formula, that is e to the power of phi theta is equal to cosine of theta plus I sine theta. We will use this one repeatedly, so that the base case could be for n is equal to 2. Just n is we are informed here that is n is starting from 2, so that let us see whether the given argument or simply this theorem is valid for n is equal to 2 or not. So when we substitute n is equal to 2 for n, we have e to the power of phi theta 1 times e to the power of phi theta 2 is equal to just the product of these two. That is because I to the power of e to the power of I theta 1 is equal to cosine of theta 1 plus I sine theta 1, and e the power of I times theta 2 is equal to cosine of theta 2 plus I sine theta 2, so that the product of these two could be this one, just multiplying both terms of the this term by in the first and second term of the first complex number e the power of I theta 1, we have this one. And then collecting terms or simply that can be combined together, we have cosine of theta 1 plus theta 2. That means we have cos theta 1, cos theta 2 here, and sine theta 1 times sin theta 2 could be combined to be this one, that's simply cosine of theta 1 plus theta 2 by using that of double angle formula. And this one that's simply enclosed by the bracket here, it could be, it becomes I times sine of theta 1 plus sine of theta 2. So that this will have of this form that is simply cos theta 1 plus sine theta I sine of theta 1. Therefore, this could be written as e the power of I into theta 1 plus theta 2. Then the inductive step could be, that is here we have seen that is the theorem holds true for the first value of n, that's simply for n is equal to 2. So let's assume that the theorem holds true for n is equal to k whenever k is an arbitrary natural number greater than 2. So that it becomes e the power of I theta 1 times up to e the power of I theta k is equal to e the power of I into theta 1 plus theta 2 plus up to this one, that is theta k. Then we need to check whether the theorem holds true for the next natural number, that is n is equal to k plus 1. We have here e the power of theta 1 times e the power of theta k. It was just previously for k, and which was identical with e the power of theta 1 plus theta 2 plus theta k. And then this could be obtained just by obtained from the previous one. For n is equal to k, both sides by multiply both sides by e the power of I theta k plus 1 times here e the power of I theta k plus 1. Then using the base case, we have this one, that is e the power of I into theta 1 plus theta 2 up to theta k plus theta k plus 1, just we have here, is equal to e the power of theta 1 plus theta 2 up to theta of k plus 1. Therefore, for n is equal to 2, 3, 4 up to like this here, we have e the power of I theta 1 times e the power of theta 2 up to e the power of I theta n is equal to e the power of theta 1 plus theta 2 plus theta n, which is the last step for the proof of this theorem by using that of mathematical induction. Question number 4a. We have here, that is, we are asked to just show that cosine of 3 theta is equal to cos cubed theta minus 3 cos theta times sine squared theta. So just to show this one, using Demoivres formula, we have cos 3 theta plus I times sine 3 theta is equal to cos theta plus I times sine theta to the power of 3. Therefore, expanding the binomial theorem, that's simply expanding this expression, that's cos theta plus I sine theta at the power of 3. We have this thing which is the power of 3 theta plus 3i cos square theta sine theta plus 3i square cosine of theta sine square theta plus I cubed sine cubed theta. Then this could be further simplified to cos cubed theta plus 3i cos square theta sine theta minus this minus I times sine cubed theta. And again, then equating the real and the imaginary parts of this complex number, that is the real part, which is an expression without the imaginary number, and we have cos cubed theta here, cos cubed 3 theta. That means just the expanded form of this one is equivalent to here. We have cos 3 theta here, which is equal to the real part from this one, that is cos cube theta here we do have, and minus 3 cos theta sine square theta, but the rest, this and this one are imaginary, so that let us equate cos 3 theta taken from this one is equal to cos cube theta minus 3 times cos theta sine square theta. Therefore, just we have we are able to show that cos 3 theta is equal to cos cubed theta minus 3 times cos theta sine square theta, which this one is obtained from the binomial expansion of this one, that is cos theta plus I times sine 3 theta. Similarly, similar question, but with different trigonometric value. We're asked to just show that sine 3 theta is equal to 3 times cos cubed theta sine theta minus sine cubed theta. And again, from the previous slide, we have the expanded form of cos theta plus I sine 3 theta to the power of 3, which is equivalent to that of this one. So that equating the imaginary part here, we have 3 sine theta, and because this is the imaginary, 3 sine theta is equal to the imaginary part taken from this expansion could be, that is containing with I, that is the term which is enclosed by the bracket here. We have 3 times cos squared theta sine theta minus 3 cubed theta, which is identical with this one. Therefore, alternatively, using sine squared theta is equal to 1 minus cos squared theta, we are able to show that sine 3 theta is equal to 3 sine theta minus 4 sine cubed theta, which is equivalent to this one. You can check by yourself. Okay, question number that is show that for all complex numbers z1 and z2, show that the norm of z1 times z2 is equal to norm of z1 times norm of z2. That means the norm of the product of two complex numbers is the same as the product of the norms of the individual complex numbers. Using the identity that we know here, that is the square of a norm of a complex number is simply the same as the complex number multiplied by its complex conjugate. And then the square of the product of z1 and z2, that is the square of the norm of the product of these two complex numbers is the same as the product of the complex numbers multiplied by the complex conjugate of the two, that is the individual complex numbers, so that this product could be that is commutative property. We have z1 times z1 bar multiplied by z2 times z2 bar. And then we have z1 times z2 bar is equal to norm of z1 square plus square of z2 square, the z2 square. So because z1 times z1 bar is norm of z1, norm of z1 square, and z2 times z2 bar is the square of norm of z2. Therefore, taking the square root of both sides of this equation, we have, since it is norm, that is simply positive, so that taking the square root of both sides of this one will give us norm of the product of z1 and z2 is equal to the product of z1 and norm of z2. Question number 5. Show that for z different from that of 1. We have 1 plus z square plus z to the power of n is equal to 1 minus z to the power of n plus 1 over 1 minus z for z different from that of 1. Therefore, this geometric series actually with the first element, that's g1 is equal to 1 and r is equal to z, so that let us start by letting s is equal to 1 plus z plus z square plus this one that's simply z to the power of n, which is the last term. And then multiplying both sides of this equation by z, we have z times z times s is equal to z times 1, that's z times z squared, z cubed plus z to the power of z plus 1. The power of z plus 1 means this one, that is z to the power of n multiplied by z. We have this one, that is z to the power of n plus 1. Then let us subtract that simply. This one, that's simply s and z times s, so that we can have s minus zs, which is zs minus zs here. And subtracting term by term, this one zs from here, we have 1 minus z, and that means we have z here, we have also z here, z square, so that what we are left here is the first term of this one, that's simply 1, because there is no 1 here, and the last of this one, that's z to the power of n plus 1, which is 1 minus z to the power of n plus 1. Then taking s as a common factor here, we have s into 1 minus z is equal to 1 minus z to the power of n plus 1. Then taking or simply dividing both sides of this equation by 1 minus z just to obtain s, which is defined to be this one, that is the original expression given here, so that we have s is equal to 1 minus z to the power of n plus 1 over 1 minus z, which holds true for, or simply which is defined for z different from that of 1. And therefore, they hit the proof. And the next one is on the extraction of roots. That's question number 6. We're asked just to find the square root of z is equal to 9i. The square root of z is equal to 9i. So the first, in order to find the square root of this one, let us use or simply change this complex number into a polar form. The polar form of this one is z is equal to 9 times e to the power of 5 times pi over 2, because here r is the square root of 9 squared, that's simply 9, and theta, because the real part of the complex number is theta, so that it is on the positive y-axis, that's simply the so that the angle, that's the argument, becomes pi over 2. Then the square root, that is the square root of z is equal to the square root of that simply r times e to the power of I into pi over 4 plus k pi, wherever k is equal to 0 to 0 and 1. And therefore, for k is equal to 0, we have the square root of z is equal to 3 times e to the power of pi over 4, because whenever k is 0 here, it becomes 0, so that we are left only pi over 4 times I, which is I times pi over 4, which is equal to 3 times cosine of pi over 4 plus I times sine of pi over 4, which is equal to cosine of pi over 4 is radical over 2 over radical to over 2, so that's 3 times radical to over 2 plus I times 3 times radical to over 2. So that this is the first possible square root of this given complex number, that is it is equal to 9i. And for the other value of k, that's simply k is equal to 1. If you substitute 1 in the place of k here, that's simply k pi. We have the sum of pi over 4 and pi. We will obtain 5 pi over 4, so that's the square root of it becomes 3 times, that is the square root of 9, the square root of r, that means e to the power and e to the power of I times 5 pi over 4, which is equal to 3 times cosine of the argument 5 pi over 4 plus I times sine of 5 pi over 4 again, which is equal to negative 3 radical 2 over 2 minus I times 3 radical 2 over 2. So that is and the third quadrant, an angle which is found in the third quadrant. Therefore, the second possible square root of this complex number is said to be this one, which is negative 3 radical 2 over 2 minus I times 3 radical 2 over 2. The next one, that is find the cube root of z is equal to negative 8i cube root. So that, like the previous one, first the polar form of this complex number could be r is, since it has only imaginary parts, it could be 8, which is obtained from the square root of minus 8 squared. And the argument is pi over 2, since the real parts of the complex number is 0, so that it could be on the positive y-axis. So that the cube root of using the formula, the cube root of z is equal to the cube root of r, that is cube root of 8 times e to the power of I into negative pi over 6 plus 2k pi over 3. And here that is negative pi over 2 over 3. So that k is running from 0 to n minus 1, that's simply 0, 1, and 2. So that for k is equal to 0, that is the first cube root of this complex number will be obtained to be the cube root of 8 is 2, e to the power of negative pi over negative I pi over 6, since we are taking k to be 0, so that this product becomes 0, so that we are left only negative pi over 6. So that the equivalent with 2 into cosine of pi over 6 minus I times sine of pi over 6. Cosine of pi over 6, I don't know, it is radical 3, and sine of pi over 6 is minus 1. So that's, we're left at this one, that's radical 3 minus I tilde. So that this could be the first possible cube root of this complex number, that is it. Similarly, when we take k is equal to 1, it becomes to the power of I times pi over 2. Is equal to 2 times cosine of pi over 2 plus I times sine of pi over 2, which is equal to I. That means already cosine of pi over 2 is 0, but sine of pi over 2 is positive 1, so that the second cube root of this complex number, z is equal to minus I, could be positive 2i, which is pure imaginary. And lastly, the third could be obtained by letting k is equal to 2. When k is equal to 2, that's simply here, we have 4 pi over 3 plus minus pi over 6, which is 7 pi over 6. So that it becomes to the power 2 times e to the power of I 7 pi over 6, which is 2 times cosine of 7 pi over 6 plus I times sine of 7 pi over 6, which is equal to minus radical 3 minus I. So that the cube roots of this complex number could be positive radical 3 minus I, this pure imaginary number, that is 2i, and negative radical 3 minus I. The next one, that's question number 8. It is solving this equation, that is z to the power of 3 over 2 is equal to 8i. So we need to find that simply the variable here is a certain complex number, it may be written in the standard form. So just to have the value for z, let's rewrite this one, that's simply z in the form that's simply 8 times e to the power of I pi over 2. That means when we change this one into this form, that is r is the square root of 8 squared, that is 8, and the argument of this complex number, that is 8, I could be a pi over 2, so that it becomes this one. Then taking or raising 2 over 3 to both sides, we have z is equal to 8 e to the power of I pi over 2 times the power of 2 over 3 is equal to this expression, which is 8 times to the power of 3, 8 to the power of 2 over 3 times e to the power of I pi over 3. Then this could be further simplified to 8 to the power of 2 over 3 means, I think, to the power of 2, that is already 4. And we have this one that simply it becomes 4 times. If we substitute here, that's simply this one, e to the power of I pi 3 is equal to 4 times cosine of pi over 3 plus I times sine of pi over 3, which is equal to cosine of pi over 3 is, I think it is 1. 1 over 2. And this one could be sine of I times sine of pi over 3, which could be further simplified to 4 plus 2i times radical 3. Then also consider the periodicity. We become a periodicity that simply with certain period. Z is equal to 4 times e the power of I into pi over 3 plus 4k pi over 3 whenever k is running from 0 to this one, that is 2. And then the three solutions could be that is 4 times e the power of I pi over 3. And second could be 4 times e the power of 5 pi over 3. And the last one could be 4 times e the power of I 3 pi, which is equal to minus 4 pi. Because cosine of 3 pi, sine of 3 pi is already 0. The next one, question 8b. Again, it is solving this equation that is z squared plus 4i is equal to 0. To have a solution for this one, let us take this one for I to the right side, and it becomes z squared is equal to minus 4i, which is equal to 4 times e the power of minus pi over 2 in the Euler form. Because here the real part is 0, so that the argument is pi over 2, and r is the square root of minus 4 squared, that is already 4. Then taking the square root of both sides of this equation, the square root of z squared is 8, and the square root of this one in Euler's form could be 2 times e the power of minus pi over 4 plus, that is minus pi over 2 over 2, that means plus I k pi when k is running from 0 to that of n minus k minus 2, that is 0 and 1. Therefore, for k is equal to 0, we have z is equal to, if we substitute k0, this becomes 0, and minus I pi over 4 will be left on the exponent of e here. Therefore, that becomes 2 times e the power of minus pi over 4, which is equal to 2 multiplied by e the power of minus pi over 4 could be cosine of pi over 4 minus I times sine of pi over 4. Cosine of pi over 4 is radical over 2, and sine of pi over 4 is again the same, that is radical 2 over 2, so that when we distribute 2 over here, we have radical 2 minus I times radical 2. And therefore, for k is equal to 1 again, the second possible root of this equation, we have z is equal to, if you substitute k is equal to 1 here, we have minus I pi over 4 plus I pi. So that we will obtain z is equal to 2 times e the power of I 3 pi over 4. 3 pi over 4 is already the sum of minus I pi over 4 and pi. So that it could be 2 into e the power of I 3 pi over 4 could be cosine of 3 pi over 4 plus I times sine of 3 pi over 4, which is equal to, again, this is radical 2 over 2, radical 2 over 2, but this one is negative, so that's minus radical 2 plus I times radical 2. Therefore, this equation have two roots. The first root is radical 2 minus I radical 2, and the second root could be negative radical 2 plus I radical 2. The third question on solving equation again, we have this one, that is z squared minus 4a is equal to 0. Again, simplifying or simply taking for I to the right side of this equation again. Sorry. We have this one, that is z squared is equal to 4i. 4i in Euler form could be, that is 4, which is r times e the power of I pi over 2. Then taking the square root again, usual like the previous one, we have z is equal to 2, that is the square root of 4 is 2. And e the power of I pi over 2 could be e the power of I pi over 4 plus I k pi when k is possible values of k are 0 and 1. So that for k is equal to 0, z is equal to 2 times e the power of I pi over 4. That is, this is already 0. But this could be 2 into cosine of pi over 4 plus I times sine of pi over 4, which is this one, that is radical 2 plus I times radical 2. This is the first root of this equation. Second root will be obtained by letting k is equal to 1. When k is equal to 1, z becomes this one, that is this I times pi over 4, which is the sum of this one pi over 4 and pi. So that it could be 2 into cosine of 5 pi over 4 plus I times sine of pi over 4, which is equal to this is negative radical 2 over 2, but this is also negative. Then when we distribute this one over the trigonometric values of cosine and sine of pi over 4, 5 pi over 4, we have negative radical 2 minus I radical 2. So that's the two possible root of this equation could be radical 2 plus I times radical 2 and negative radical 2 minus radical 2. Okay, that is the end of the solution. Thank you for watching.